Good morning, students. Today we are going to talk about some more fun stuff. This is the second section of Biology 101. So it's lecture 2, and today we'll be looking at other things. Last time we talked about life, and we just defined life. We defined it as a chemical system. But today we're actually going to look at chemistry. We're going to look at the chemical system that defines life, that makes up life. First, of course, as always, definitions. Life is composed of matter. And then again, what is matter? Matter is defined as anything that takes up space and has mass. But space we all do kind of understand, but that's in three-dimensional space. But what is mass? And so again, sorry, it's one of those convoluted definitions. Mass is an intrinsic physical property of a body, and that resists acceleration by a force. So if you remember, this is Newton's formula here. It's all part of Newton's formula, which we usually write as like this. But here I am. I have just changed it around, so this goes here, and it becomes F over A, and that's what I've written here. Okay, so what we have is the definition of mass. It's the force that resists acceleration. It's the physical property of a body, and it is expressed as a force that resists acceleration. And usually we take this to be the amount of matter in a body. Mass is usually the weight, as long as we're talking about speeds of acceleration, not close to the speed of light. Because when we look at the speed of light, notice here, mass is no longer this force. It is now E divided by the speed of light. Speed of light squared. So C is, as we know, is the speed of light, and E is just energy. So if we're not talking about those speeds, and we're just talking about Earth, then we don't have to worry about anything else. All we know is that mass is just the weight. A body does not have to have weight, but it does always have mass. An astronaut, when he's out in space, doesn't have any weight, but he's still there. He has mass. So mass is an intrinsic physical property. It is not like weight. Mass is conserved. It doesn't change through time. The weight, however, is expressed as the gravity of wherever that mass is. So the force of gravity is constant on Earth, but on other planets or elsewhere, it will be different. But since we are generally talking about the Earth, we will take weight and mass as generally being equivalent. Weight is defined as the amount of resistance to free fall due to the force of gravity. And here we can see that here's that same formula that I showed you before. Force is equal to mass times acceleration. So if this quantity becomes bigger, if the acceleration increases, then this quantity has to become smaller because there's an equal sign, right? So this has to stay a number, whereas if we mess around with these numbers, the product still has to equal this number. Okay, so usually what we do is we represent mass like this. Weight is equal to minus mass times acceleration. And these are concepts that have gone back in time, all the way from Galileo on to Newton and other scientists. These concepts have been worked out for centuries. Universally, every object has gravitational mass, and therefore every object generates a gravitational field. we are going to talk about elements. So now that we've sort of have some sort of handle on what life is, it's matter. And what matter is, it has mass. And what mass is, it has some resistance to acceleration and to a force. But it also is a physical intrinsic property. So even if there's no weight, there's always mass. And mass is composed of matter, and matter is made out of elements. So elements, what are they? They're pure chemical substances with only one kind of atom. An atom is a basic unit of matter. It has a dense nucleus of neutral and positively charged particles, and these are surrounded by a cloud of negatively charged particles. Atoms are arranged in a table of 18 columns and 7 rows, and they're classified by the increasing number of protons in the nucleus. So you've seen this arrangement of elements as the periodic table. There are 92 naturally occurring elements on Earth. The first element in the periodic table is hydrogen, which is the most abundant element in the universe. Hydrogen has just 1 electron and 1 proton. So in the periodic table, all the charges are balanced. So if there's this many protons, it has to be that positive charge is balanced by that many electrons, which are negatively charged. The next element, the second element in the periodic table, is helium. Helium has 2 electrons and 2 protons. So you see the addition of one tiny little electron, and notice how small this mass is. Look at this mass. It's itty bitty teeny tiny, 10 to the negative 28 grams. 1 electron makes such a difference. It's a completely different element. Helium is nothing like hydrogen. And because it has another electron, it has to have another proton. So it is now a little bit heavier. Atoms have 3 types of subatomic particles. So you sort of got an idea of that. There are electrons, protons, and neutrons. Neutrons have no charge. Protons have a positive charge, and electrons carry a negative charge. And here again is the periodic table. We looked at it before, and we notice here that the first element is hydrogen, and then the second element is helium, and then we go down this row: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. And we keep going down the periodic table like that, and we cover all the elements that occur on Earth. And the difference between each element is 1 proton, addition of 1 proton. I do have some links at the bottom, and we can try and see if they would actually work. Maybe not today, but we can go on to the next one. Oh, whoopsie, and that carried over. Let me just erase this. All right. Compounds. What are compounds? Compounds are very important because, yes, it's great to have an element, but what do you do with it? So you would like to bind compounds, bind elements together to get something new. A compound is made by bonding 2 elements, but in a fixed ratio. And the compound will have characteristics completely different from those of its elements, which is kind of cool, because already we see adding 1 proton makes the next element completely different from the element before it or the element after it. And then when we start bonding 2 elements, we see something that is completely different as a compound. For instance, we can look at the element sodium, and we can look at the element chlorine. Sodium on Earth is this nice soft looking rock, and you can actually cut it with a knife. Chlorine is represented in the center of this slide, and it is here liquefied. And so if we add the 2 together, sodium and chloride, we get table salt. which has none of the properties that its parents had. So notice that sodium chloride is white, sodium is not white, chlorine is not white, and the chlorine actually is poisonous. Sodium chloride is harmless. So properties of the compounds are completely different from those of the elements that compose it. Subatomic particles. Let's talk about those a little bit because those are kind of important. Neutrons and protons reside in the nucleus, and the electrons just whiz around it very, 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 very fast and form sort of like a cloud. But the neutron mass and the proton mass are almost identical, and they are measured in a unit called Daltons. So here's a picture of an element, and we have two positive charges in the nucleus. So this could be helium. And we also have two electrons, which are whizzing around at a distance from the nucleus, and they have negative charges on them. Okay, I know it looks like that they're in this circular orbit, but actually they're not. So here, when you see the circular orbit, that's just an idealization because the electrons are moving so fast. The true representation is this. It's like a cloud because this electron could go here, could go here, could go here, could go anywhere in any direction. And so at any one point, you wouldn't know where that electron is. And so we represent, to be accurate, you'd want to represent it as being in a negatively charged cloud around the nucleus. Atomic number and atomic mass. Oh, we have to know this. Atoms differ in the number of subatomic particles. We already talked about this. So the atomic number is what exactly? It's the number of protons in its nucleus. And remember, the number of protons is always balanced or matched by the number of electrons. So the number of protons and the number of electrons are the same. So the atomic number, you could also say, I guess, if you wanted to, is the number of electrons, but it's not. They're not really in the nucleus. So we just want to keep it simple. And so what we say is the atomic number is the number of protons in the nucleus of an element. However, the mass number is the sum of all the protons plus all the neutrons in that nucleus. All right, so that is something different. And atomic mass, which will be the total mass of that atom, it will include the neutrons and the protons and also the electrons, but the electrons have so little weight that you can just basically approximate the atomic mass as being the mass number, which is the sum of the protons and the sum of the neutrons. So the idea of neutrons is important. You might say, you know, they don't do anything. They just have a neutral charge. They just add weight. But they don't really do much, do they? And so how is it going to help the element in anything? Well, they do. They actually do have a voice in the fact that sometimes the element may have a different number of neutrons. So that wouldn't make it another element because the elements are in the periodic table are differentiated only by the number of protons. Okay, so if the number of neutrons somehow changes, it shouldn't, but somehow if it does change, then what is this thing called? It's not a new element, it's still the same element, but it's an isotope of that element. So an isotope is two forms of that element that differ by the number of neutrons. And radioactive isotopes usually are those that decay spontaneously and they don't want that extra neutron, so they just want to get rid of it somehow, and gradually it will decay off in tiny minuscule particles and energy until finally it's gone. but usually isotopes are just, they're not really radioactive, but some of them are. And we actually harness that in medicine. We can actually inject a dye that's radioactive, and then we can pick it up with a machine that can pick up radioactivity, or we use it to date material and to find the age of something. We can use radioactive isotopes for that purpose. A parent isotope will decay into its daughter isotope at a fixed rate, and that rate is expressed as the half-life. So half-life is the amount of time it takes for a parent isotope to decay into its daughter isotope. And what scientists do is that they measure the ratio of different isotopes at one time, and then they calculate, well, how many half-lives have passed since that fossil or that rock was formed. And half-life values can vary from seconds to days to billions of years. For instance, uranium, we know that it's pretty radioactive. Uranium-232 has a half-life of 68.9 years. So in 68.9 years, it will have decayed to half. Notice it says to its daughter isotope. And thorium, another very radioactive element, has a half-life of 7,340 years. Plutonium, on the other hand, 239, has a half-life of 24,110 years. So plutonium, if we use it, we can figure out, well, where are the daughter isotopes? And we can calculate how much are present in the material, and from there we can figure out the half-life. Carbon-15. Carbon exists in a few isotopes too, but they don't really count that much because their half-life is 2.5 seconds. So they're here and then they're gone really fast. So we're going to look at actually the structure of an atom. We're already looking at what's in the nucleus, what's around it, and we're talking about mass and we're talking about protons. But now we're going to look at energy. So an element will also have energy, and energy is the capacity to cause change. Potential energy, as you all recall, is the energy that matter has because of its location. And the electrons of any element will differ in their amounts of potential energy. So where they are, how far they are from the nucleus, will determine how much potential energy they have. So an electron's state of potential energy is called its energy level, or an electron shell. So again, this is an idealization. We all remember that the electrons do not actually rotate around the nucleus in a fixed place or a fixed orbit. But just to make it simple, we have drawn a hypothetical one orbit. And since we like to be symmetrical, they're made into circles. What we see here is on the top picture, a ball bouncing down a flight of stairs. So a ball at the top of the stairs has more potential energy than a ball at the bottom of the stairs. And so every time it bounces down one step, it's going to lose some energy. You may have noticed that if it's a bouncy type ball, it'll bounce a lot on the first step, less on the second step, and by the time it gets to the ground, the bounce is so small it's barely jumping up and down at all. And that is the analogy we're going to use to explain the atomic nucleus and the atom's structure. So as you see, the atomic nucleus has the neutrons and the protons, and then around them are the electrons. So if you look over here and you see this orbit around, this is a certain distance from the nucleus, and the electrons will be right here. So it won't be very close, but it's pretty close. And it will have a certain ground state or certain amount of energy. However, another distance away, farther from the nucleus, will be another area where electrons are usually found, and that will be the second shell. So that will correspond to this step. This corresponds to that step. Okay, so this part will be the bottom step, whereas this part will be this step, step number 2. And so the farther the electron is from the nucleus, its location is further off, so it has more potential energy, which is kind of cool, because if you go even farther to the very top step, an electron here would have way more potential energy than an electron here or here. Okay, and what we have then is also the idea that when things will come down, for instance, if there's an electron at the very top and it loses its energy, it may jump down one level and the energy is just going to float off. All right? Or it may jump down actually 2 levels and lots of energy will be floating off. Or we might lose this electron over here totally, or this one here, in bonding. So every time an electron is moved, energy has to be accounted for. And so this is something to keep in mind when we talk about the next things. The electron distribution and chemical properties. So the chemical behavior of an atom is determined by its electrons and where they reside in the electron shells. And we're going to look at the chemical, this distribution in the periodic table. So for instance, in the very first shell, you see 1 electron of hydrogen. And in the second element, which is helium, what you see are 2 electrons revolving around the nucleus. Now, when you look over here, that is just an idealization of the electron distribution diagram. We know that they don't actually go so politely like that. This I need to go over one time. So in the center, this He, that is the symbol of the element. The superscript number 2 is actually the atomic number, and the atomic mass is always at the bottom. All right, so what we have here is, let's try and erase this before something else happens. Okay, so what we have here is, in the next row, we have lithium. So in the first shell, there are only 2 seats. It's sort of like a carousel. Okay, we could just think of it as a carousel. The first shell just is a carousel with two seats. Both of them are occupied. So when the next electron is added on, or the next proton is added on, the proton can just kind of sit right there. But the electron has to go up another level because there's no room. There's no room on that level. So it has to go to the upper level, and therefore that electron will have more potential energy because it's farther away from the nucleus. Okay, so what we have here is the entire shell empty and just 1 electron sitting over there or whizzing around. In the next element, which is beryllium, it has 4 electrons. So 2 from helium, the configuration that we have for helium, they're right here. And then the other 2 are just going to go in the next shell. And when we have that, what we see is that there are more seats available in this carousel shell. Okay, this particular shell, the second shell, can actually hold up to 8 electrons. And if we go down across the row, we go all the way up to neon, we see that neon actually does have a full outer shell. The second shell is full, every seat is occupied, and there are 8 electrons. Of course, balanced by 8 protons. When we go to the third row of the periodic table, that starts with sodium. Sodium happens to have 11 electrons and 11 protons. Let's see, how did we get there? So there's 2 that we started off with, which came from the first shell. And then there's 8 that we got from neon, the second shell. And then 2 plus 8 is 10. And then sodium has 1 extra. So since all those seats were taken, then we have to go 1 shell up. And if we go 1 shell up, then that also will have 8 seats, or 8 places, 8 empty spaces for electrons to be added on. And if we go across the periodic table towards from the left to the right, we see that the last element in the last box is argon, and it has 18 protons and 18 electrons. And its third shell is now full because it has 8 in its third shell, 8 in the second shell, so 8 and 8 is 16, and 2 in its first shell, so that's 18 total electrons. This is the same picture of helium that I showed you before. The atomic number, the atomic mass, and the electron distribution diagram. And here is the first 2 elements in the periodic table, but this time they're not separated by a huge gap, but they just show how many electrons and where do they sit. And this is the periodic table again, but not the entire one. It only goes halfway. So this is split in half, and what we see here is it ends right here with 4 electrons in the second shell. There's still 4 more empty seats to go. But carbon is a very important compound element, and so this picture is just to highlight what happens when half the shell, the second shell, is full. And then this is the other half. And what we call these electrons that are sitting in the we call them valency electrons, and the outermost shell is usually called the valency shell. And the behavior of an atom is mostly determined by what these electrons are doing. The ones that are in the outermost shell and can react, because the ones that are buried deep in, they're not probably going to do much. They're already just hanging around. But the ones that are separated out, like up here, wait, let's see if I can get this slide to move. No, I can't. Yes, I can. Ah, success at last. All right, so if we look here, this shell right here is going to determine what this element is going to do, what its properties will be, what its behavior will be. Same thing over here in silicon. The outermost shell, which is the third shell from the nucleus, is going to determine what kind of properties will silicon have, will it bond with other things, and what kind of behavior will it have, and what kind of compounds will it form, and what kind of bonds will it form. Okay, so elements that have a full shell are chemically inert. Those would be the noble gases. Okay, so they don't really want to react with anything because their valencies are satisfied. They're good. They don't need to share anything with anybody. And we just do need to remember that there are not really any shells. It's really an orbital. It's just a cloudy sort of area around where the probability of finding an electron is high. So there's no really pre-described circular orbit. It's just called an orbital. Okay, and each electron shell actually consists of several number of orbitals. So, for instance, the first shell has the 1s orbital, and that's completely round. It's just a nice sphere. The second shell has a 2s orbital, which is completely spherical. It also has 3p orbitals, because 3 times 2 is 6, and plus 2 is 8, and you have to account for 8 electrons in the second shell. So these electrons will actually be in all different types of directions. If you notice the x-axis, the y-axis, and the z-axis right here. Okay, whoops. And these are how the electrons will continue to revolve around the nucleus. Okay, so if you superimpose all these orbitals, and this happens to be, let's see, what element is it? It is argon. And if you superimpose all these orbitals, what you see is this very interesting shape. This is actually where all the electrons will usually be found. The first shell, the 1s orbital electrons will be found in this area. The 2s orbitals electrons will be found in this general area, could be all the way. And the 2p orbitals, so they will be found sort of like this, that, and of course this is supposed to represent a 3D position, so there's front, back, side, and coming out of the screen into you, and so it's like a bunch of balloons. All right, this is just showing the 2 shells as a diagram. Oops. And the 2 shells are not as a diagram, not as a 2D diagram, but an actual, what we are trying to represent as an orbital. Okay, so this is more realistic. And then when we superimpose the electron orbitals, this is what a neon atom would actually look like. This is where the electrons would actually be found. All right, so now that we know where the electrons sit and where they're found, we can actually go around and bond 2 elements together, which is very, very cool, because now we can make new and more interesting compounds. Only those atoms that have valency shells that are somewhat empty, they can share or transfer electrons with other atoms with this in the same condition. And these interactions usually result in the 2 different atoms being closer together, held together by an attraction called a chemical bond. There's several kinds of chemical bonds. The easiest one, and the first one that comes to mind, is covalent. Covalent is a nice one. It's sharing. So everyone shares. There's sharing going on. You have it half the time. I'll borrow this electron for the other half of the time. And each atom will then have that electron for an equal amount of time, and it'll act at that time like its orbital is full, or its valency is full. So for instance, it will act like, it wants to act like a noble gas. So if it's missing just 1, then it'll share 1 from some other one that has, you know, maybe just the one. And so these guys will be shared, and you get a bond, because this will come closer to share it. Okay, so you will get a permanent sort of bond until some more energy is applied to dislodge it or to break it. All right. I think this is getting a little bit upset with me, so I'm not sure what is going on. Let me try and see if I can resolve this technical problem. Or not. So here we're showing the sharing, or a covalent bond, sharing of one electron, so that both electrons are being shared at this time. There are two hydrogen atoms. Remember, hydrogen only has the one electron. It really wants to have two. It would like to have two, because all elements want to act like they're noble gases. They're satisfied, they're full, every available space is taken. And that's how they would like to act. So the hydrogen is going to try and act like helium, because it wants to become helium. It's aspiring to grow up to become helium. When it grows up, it wants to be helium. But here, what we see is the two hydrogen atoms. Notice how they're getting closer together. And when they form a bond and they become a hydrogen molecule, their electrons are being shared equally by both nuclei. So a molecule consists of two or more atoms held together by covalent bonds. If you just have one bond between the two atoms, then that is called a single bond, because it just shares one pair of electrons. Sometimes you have a stronger bond. It's called a double bond, where two electrons are shared between two atoms. Okay, so sometimes you look in books, and there are these very funny shorthands, and we're going to actually look at that so we can think like a chemist and understand what chemists actually mean. So when we're trying to represent a bond, we can actually do this. We can just, we can do this. We can draw a line between the two atoms, and that will just simply represent a bond. So that's very easy, and we don't have to do very much. We could also just abbreviate it as hydrogen like this, subscript 2. Okay, so that just means the same thing as that. It just means there's one hydrogen, two hydrogen. Instead of separating them out, you could just write them together and abbreviate it as H2, which makes sense, right? Here are some common atoms in their molecular form. For instance, there's hydrogen. Okay, so that's molecular hydrogen. Here we see the two electrons being shared. You can represent this like that, or like that, or if you were a really good artist, you could actually draw them, and you could make the orbitals look like that. There is, next down the row is oxygen. So remember, oxygen has a nice satisfied inner shell, 2 electrons, so that doesn't need any sharing. But the outer shell has 6 electrons, and it really would like to have 8. And so it's going to have to share a whole bunch of electrons with another oxygen molecule to become an oxygen molecule. So how does it do it? So in this picture, you see it's sharing 4 electrons. 4 electrons are being shared between 2 oxygen atoms. That means it's a double bond. That's why we represent it like this. Okay. Then we can even, it doesn't have to be, a molecule does not have to be just between the same element. It could be between different elements. After all, why are we even trying this? We want to have fun and make more compounds. So we can combine 2 hydrogen with oxygens because oxygen would like to have 2 more electrons. So it could either get a double bond and get it from another oxygen, or it could just use 2 hydrogen atoms and become water. And this is an outstanding compound. This is one of those magical compounds that it's just has so many wonderful properties for life. So we can represent hydrogen, water like this in a dot diagram, or just where the bonds are. Or if you wanted to really make a picture, you could do it like, notice that the great big red one, that is the oxygen atom. Oxygen atom is much, 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 much bigger than the hydrogen atom. So the hydrogen atoms are sort of like, glommed onto its side. This is not the case in methane. Methane has 1 carbon atom. In the second shell of carbon, it has 4 electrons. So it really wouldn't like to have 4 more electrons and borrow them from somebody else, or maybe for somebody else's, as in this case, where it is actually borrowing them from hydrogen to become methane. And what you see here is that there are 4 electrons being shared, and right here it is represented like this. So all the electrons for carbon, the 4 electrons for carbon are written down here, and the 4 electrons from hydrogen are written over here. And so it looks like everybody's happy, because if you just look at, if you pretend that this guy isn't there, that's not there, that's not there, then carbon looks really, 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 really happy because it has 8 in its outer shell. And if you look at just the hydrogen, like this guy, then it looks like the hydrogen is really, 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 really happy because it has 2 happy electrons in its outer shell, like it always wanted to be, because he wants to be like helium. Why he wants to do that? That's just because he does. And if you actually wanted to represent the formula for methane like this, you could also do that, in which you'd put carbon in the center and the 4 hydrogens equidistant around it, because methane is a symmetrical molecule, as you can see in this space-filling model, where it is different from hydrogen and water because the oxygen is so much bigger. Here, the pull is the same on all four atoms of hydrogen. So it is not a distorted looking molecule, and it's just equal sharing, and these are all covalent bonds. All right, so this is just another breakdown showing you one by one what this is. Let's see if I can get rid of this. No, maybe not. Yikes. All right. And this is just so you can remember how oxygen looks like when it's in the molecular form. And this is water, a compound. And this is methane, also a compound. And you can represent it in an electron distribution diagram, a Lewis dot structure, a structural formula, or a space-filling model. Or you could just write it out, spell it out as methane. Or just count up how many atoms of each type they have and write them out like that. So covalent bonds can form between atoms of the same element or atoms between different elements. And a combination of 2 or more different elements will create a compound. The bonding capacity is called the atom's valency. So that's determined by how many electrons it has in its outer shell. Atoms in any molecule attract electrons to some degree or another. And this characteristic of an atom is called electronegativity. It's the attraction for electrons by an atom in a covalent bond. The more electronegative an atom is, the more strongly it's going to pull that shared atom towards itself, as you saw in the case of water. So over here, whoops, oxygen is very highly electronegative. Hydrogen, not so much. So he's going to pull the shared atom to him to stay in his side longer than the poor little hydrogen atoms who are trying to share too are going to be able to pull them back. Covalent bonds can also be polar or nonpolar. Okay, so in because of this electronegativity, if a covalent bond is polar, that means that the atoms are not shared equally. They are shared, but the electrons are not spending as much time as they should with both types of atoms. They're spending more time with one and less time with another, and that is called a polar covalent bond. In a nonpolar covalent bond, the atoms are share the electrons equally. So that would be this guy here. This is a nonpolar covalent bond. Everything is being shared equally. Everyone's nice, all right? So here we have equal sharing, and that's why methane is a nice symmetrical molecule with polar and nonpolar bonds. Oops. Okay. The water molecule again comes back here. Now let's look at this a little bit carefully. So when we put the symbol for electronegativity, we always use, oops, that. And then since the oxygen atom is more electronegative than the hydrogens are slightly more positive. Oops. All right. Sometimes there is no sharing. So some atoms just don't want to share. And in that case, they'll just strip it. They'll strip the electron from their partner and keep it. And an example of that is sodium chloride. So sodium chloride, the table salt that we saw earlier, over there we have one. Let's go back to the periodic table. And what we see is oops, gone too far. No, wait, come back. All right. Sorry about that. So we were talking about sodium and chloride. So this is sodium. Oops. Sodium. And chloride is here. So chlorine just needs one more. It needs this one electron to complete its outer valency. Sodium only has the one. Okay. So if these two combine, you will get table salt, and you will get something called sodium chloride. However, the pull on this one lonely electron is so much that the sharing is simply just not possible. And so what sodium will do is it'll just donate its one electron to chlorine, and chlorine will be very happy to have its orbital shell completed. Sodium will have lost one, but it will still be happy because its outermost shell is now perfect. It may not be the one he wanted, but he would have needed 7 more electrons to get the noble gas configuration. But in this case, it's just simpler for him to give it up and get the noble gas configuration of the previous one, not aspire to go forward, but to go backwards. So I'm not sure what is going on here, but things are not doing well. Oops, oops. This is a picture of sodium chloride, how the atom behaves. So the electron in red is going to be donated by sodium to chlorine, and it will form a new compound. Sodium will therefore have a positive charge. And why is that? That's because, remember, all the charges were balanced. Now there's one extra proton in the nucleus, and it's not balanced by the electron because it gave it up. It donated it to chlorine. And chlorine will have a negative charge. And why is that? Because there's one less proton in the nucleus, and so it carries a negative charge. Let's see if I can actually get this to work. Maybe, maybe not. No, not today. All right. Anyway, so here what we have is the element sodium, 11 protons, 11 electrons, the element chlorine, 17 protons, 17 electrons, and what will happen is the outermost, this will be donated here, so you'll have 10 electrons and 18 electrons here. And that is why, because of this mismatch, you have a positive charge, and because of this mismatch, you have a negative charge, a net negative charge. So an ionic bond is one that ends up with charged particles because of the imbalance between protons and electrons. So the positively charged ion is called a cation, the negatively charged ion is called an anion, and the ionic bond is defined as the attraction between an anion and a cation. Ionic compounds are usually salts, like sodium chloride. Other salts are found as crystals. Here is a very pretty picture of sodium chloride. It looks not so symmetrical in the picture, the real picture on the left, but when we actually look at every molecule, it is a repeating pattern, and it's very, very symmetrical. Besides these bonds, there are weak chemical bonds. So we have ionic bonds, which are very strong. We have covalent bonds, and they can be single, and they can be double, and they can be very strong. And there's sharing, and there's polar bonds, and there's polar covalent and nonpolar covalent. And they're also pretty strong. But you can have weak chemical bonds, and weak chemical bonds, now why would they be useful? They are very useful because to break a bigger bond you need a lot of energy. But if you just had the weak bond to begin with, and it was just like sort of a temporary thing, then you know, it's very easy to break this, and you don't have to spend a lot of energy. So the strong bonds, you do need those, the covalent ones, because they're just going to hold the cell or the body together. But large biological molecules usually are held in the right forms by weak bonds because these can be reversed. Hydrogen bonds are very, very weak bonds. That's when a hydrogen atom is covalently bonded to another electronegative atom, and usually that's oxygen or nitrogen in nature. So this is called a hydrogen bond because it is specific. It is a covalent bond, but it is called a hydrogen bond because it involves hydrogen. All right, so the top picture is of water, and the bottom picture is of ammonia. And the blue ball you see in the center is supposed to be the nitrogen atom. Other weaker forces than hydrogen bonds are van der Waals interactions. So van der Waals interactions are very, very, very weak interactions. If the electrons are just sort of piled on one side of an atom or a molecule, they will actually create a negative part to that molecule, and then they will attract another molecule that has a positive part to it. And so that will be called a van der Waals interaction, and the molecules are held close because of that. And you may think, well, who cares about these? But actually, these are really good because that's how lizards can scamper on the walls. They make these very temporary bonds that are van der Waals interactions with the wall and their toes, and they break very easily, so they don't have to keep on spending a lot of energy. They're not stuck and have to yank their feet off. They can just run around on a wall like that, you see. So van der Waals forces are very impressive. They may be very, very small, but when you have a lot of them, then a lot of them will actually be very impressive. All right, so we know that a molecule's shape will determine its function, and it's also determined by the orbitals that the component atoms have. In the covalent bonds, this S and P orbitals actually may hybridize, and this is something that is very cool. They could create new shapes, new areas where the electrons will actually sit. So it isn't simply, we'll just add it on, but actually they become completely different shapes, and you get a hybrid molecule. For instance, 3p orbitals, you'll get a tetrahedron instead of what you saw before. Okay, so here the orbitals have hybridized, and instead of having 3p orbitals in the star-shaped form, you could get 4p orbitals in a tetrahedron form. So the electrons will actually be whizzing around in different areas. Okay, so this is just to show you where the double bonds are, where the single bonds are. Notice how these are double bonds here. Oops. No, that's not actually a double bond at all. And that's not actually a double bond. That's just a stick. All right. My bad. I'm going to try and see if this works. Today there doesn't seem to be a lot of luck in this because there's some sort of a glitch with the technical stuff. So I won't be able to show you these very neat ways to look at orbitals, but I think you can click on them perhaps on your own and you can look at them. Why is the molecular shape crucial in biology? Because the shape will determine how the molecules will recognize and respond to each other. And sometimes molecules copycat another molecule's shape, and the body will get fooled and won't recognize it's not actually that molecule. So they will have the same result. Opiates like morphine will have a similar effect to naturally produce endorphins because their shapes are very similar, and the brain will have the receptor which won't be able to distinguish one from the other. Chemical reactions are the result of making and breaking chemical bonds. And so, now that we understand bonds, we understand the molecular shape, we understand the atomic shape, now we're going to start reacting all these things and see how do things form. So in the beginning of any chemical reaction, you have some starter molecules, some molecules that you're going to start out with. Those are called reactants. They are going to actually react with each other. And the final molecules of any chemical reaction are called products because they're completely different from the initial molecules. Here is a picture of 2 hydrogen molecules and 1 oxygen molecule. And they are already bonded with each other, okay? So the hydrogen, as you see on the left-hand side, right here, they already have bonds, okay? The oxygen has a double bond with another oxygen atom, so they're good. However, if you get them to react and you carry out a reaction between them, you will get this bond to break, that bond to break, and new bonds to be formed and new products formed. So instead of hydrogen and oxygen, which are 2 gases, you'll get water, which may or may not be a gas at that point. So when we talk about life and we talk about chemical reactions, one of the most important chemical reaction is photosynthesis. That is a chemical reaction where bonds are broken and new bonds are formed. But this is where the cool part is. So what we have is, carbon dioxide, and we have water, okay? And we take these 2 compounds and we react them together, and carbon dioxide is a very stable low energy compound. Water is a very stable low energy compound. But if you can get them to react, and the only way you can do that is by adding solar power, then you get this compound, which is gorgeous because it is full of energy. It has a ton more energy than either of these compounds. And of course, you'll give off some oxygen too. So this is a really, really cool way of capturing the sun's energy, putting it into bonds, and then using it later by breaking those bonds to power life. And here is a very pretty picture of photosynthesis going on in plants. Most chemical reactions are reversible, which means that you can get the products and then you can cool the apparatus down. You get the initial products, initial reactants again, if heat was the only way you could have gotten the products. So you can reverse them. But usually when we talk about chemical equilibrium, it's when the number of products is not going to increase, okay, because the forward and the chemical backward reactions are occurring at the same rate, so you get the same number of products that you're going to get from this reaction, and you have reached a stable point, and that stable point is called chemical equilibrium. All right, so this is just basically review. And we're just going to end up with talking about nucleus. So this is a helium atom. You see the nucleus, it has protons in it and neutrons, which have no charge, but do determine if it's going to become an isotope or not. The protons actually determine what element it's going to be. And the electrons sit in an area or a shell outside the nucleus, and they have negative charges. And then we understood what were bonds, and we tried to make new compounds, break bonds, create bonds, and we understood what a single covalent bond was and a double covalent bond where there's sharing going on. And then when there's no sharing going on, that is an ionic bond where each atom will actually acquire a charge because it gave up or it took in an extra electron. Okay, and then we looked at Lewis dot structures and how to represent bonds in shorthand like chemists do. All right.